All right, let's continue talking about volumes. Volumes still. So last time we talked about the disk and the washer method, and I said this a couple times that they're the same. What I meant by that was that the washer method, well, I should say the disk method really just is the washer method when your inner radius is 0. So I'll just point out very generally, washer method, you're simply thinking of doing pi times the integral of your big radius squared minus your little radius squared, d whatever. That's kind of it, right? You just have, I mean, you have to have like the right limits of integration. But that's the idea. Get your big circle area minus your little circle area, and then you add up all the volumes of the slices to get the, right, it's your area times your thickness, which is the volume. And similarly, the disk method, you end up getting pi times your integral from a to b of your big radius squared minus your little radius squared, which is 0, which we don't write. But really, that's why I was saying they're kind of the same method, because you're always just taking an area of a circle minus the area of a smaller circle. The smaller circle might have an area of 0 if it's the washer method, this disk method. So let's go ahead and look at, let's look at this example. So we talked about revolving kind of either way. And the one thing I'll remind you of for both the washer method and the disk method is that in these volume methods, the strip that we're going to draw must be perpendicular to the axis of rotation. So let's look at an example. Let's say, sure, we're going to revolve the region bounded by, sure, what do they got here? Sure. Y equal to the square root of x and y equal to 1/4 x around and we'll do a few of these as well. And we're just going to set these up. We're not going to actually calculate them because we really just want to talk about, oh God, words, talk about the setup. So the first thing will be around the x-axis. And we'll try not to draw this every time. So here's my region. It's y equals root x, which looks vaguely like this. And it's y equals 1/4 x, which looks like a straight line through the origin. And this point of intersection here is, well, if root x equals 1/4 x, okay. Typically, when you have graphs like this that intersect somewhere, usually the point of intersection is nice. They're not trying to make you do something ridiculous. So I'm just going to start thinking about what square numbers can I plug in for x to get a nice number out. Let's see. Square root of 4 is 2. 1/4 times 2. Nope, that doesn't work. Square root of 16 is 4. 1/4 times 16 is 4. Oh, that's the point of intersection when x is 16 and y is 4. Yeah, you could also square both sides and solve this relatively easily, but sometimes it is useful to just guess the nice answer as opposed to try to work it out because there's other problems where it can be a little bit more gross. All right, so we're going around the x-axis, which means we want our strip to be a vertical strip. Our outer radius is the further away function. Our inner radius is the closer function. So the closer function being, right, this is your closer function. This is your further away. So the volume, the integral for the volume of this revolution, oh my gosh, words. The integral for the volume of this solid of revolution should be pi times the integral. My strips go as far left as 0, as far right as 16. Big radius squared, that's going to be the square root of x squared minus the little radius squared. It's going to be 1/4 x quantity squared. I would not simplify this at all if someone asked me to just set this up on an exam, because leaving it like this really shows them that oh yeah, it's pi times your big radius squared minus pi times the little radius squared. Even though square root of x squared does simplify nicely as x, I wouldn't do that if they said just to set it up unless they specifically gave me instructions to simplify it. Obviously, if we were going to integrate this, we would totally simplify it and then anti-differentiate, plug in some integration, et cetera, et cetera. But we're not going to. So questions about that before we rotate around a few different axes. Okay, let's look at the same region, but now we're going to revolve around the line y equal to -2. And I think I lied because we're probably going to draw it every time, or at least I'm going to draw it every time. Doesn't have to be perfect, just has to be approximately looking like the thing I'm working with. So there's my axis of rotation. It's a horizontal line, meaning my strip should still be vertical because my strip should still be perpendicular to my axis of rotation. So now check this out. My radius has gotten bigger. My inner radius is now not just the function y equals 1/4 x, it's the difference between my function and the axis of rotation. Same is true for the larger radius as well. So to me, it looks like my large radius is going to be the square root of x minus -2, and my inner radius or my smaller radius is going to be 1/4 x minus -2. It's the difference between your function and your axis of rotation. Come on in, have a seat. So setting up our integral, the volume is going to equal pi times same limits of integration, still as far left as 0, as far right as 16. And then it's my large radius squared minus my smaller radius dx. It probably would be fine to simplify that as root x plus 2 and 1/4 x plus 2. But again, I'm really trying to show the person that's reading my work that I know what's going on, that I'm finding that radius by subtracting or finding the difference between root x and -2 or 1/4 x and -2. For the disk/washer method, if you get oh my gosh, if you get the order subtraction out of order, it's actually not a problem. That said, I would encourage you to try to get it in the right order. What do I mean by this? Well, if you're subtracting two things and then squaring it, it doesn't matter if you did 1 minus 3 and got -2 squared or 3 minus 1 and got +2 squared. The end result's still going to be the positive number. So for the disk or washer method, if you happen to get things out of order when you're subtracting, it's not the end of the world. But it does make a difference when we start talking about the shell method, which way you subtract things. So it's good to just try and do it the same way every time. What I really want to point out here is if we go around the line y equal to 7, how that's going to change things a bit. This is why I think for these ones, you should draw the picture every time. Because without the picture, it's really hard to see kind of which thing is closer and which thing is further away. And it's probably more work to try and like plug in a point and then see which thing's bigger or smaller. It's just easier to draw the darn thing. So then my axis of rotation is way up here at y equal to +7. Once again, I'm still drawing my strip vertically because it has to be perpendicular to the axis of rotation if we're doing the the disk or washer method. But now look, the function that's further away has changed. My outer radius now is the difference between my axis of rotation and the function y equals 1/4 x. And my inner radius is the difference between y equals 7 and the square root of x. So here I would say my outer radius is 7 minus 1/4 x. And my inner radius is 7 minus the square root of x. And that is the correct order of subtraction because you should be subtracting a bigger thing minus a lesser thing so that we end up with a positive radius, not a negative radius. Even though it'd be fine if we accidentally got it wrong. But we're not. We're going to do it right. So then, same deal. Our volume here is going to be pi, still the integral from 0 to 16, big radius squared minus little radius squared. All right, now we're going to go the other direction. We're going to spin around axes that happen to be vertical instead of horizontal. We'll do one or two of those, and then we'll finally start talking about the shell method. So, still the same good old region. So now if I go around, say, the y-axis, now my strip has to be horizontal. And I rotate it around, I'm going to get a washer. And my inner radius is the distance to the blue function, and my outer radius is the distance to the red function. So my inner radius here should be, well, let's see, the blue function was y equal to the square root of x. It's going to become x equal to y squared. My red function was y equal to 1/4 x. It's going to become x equal to 4y. So my inner radius here should be y squared minus 0, if you like, right? The difference between my function and the axis of rotation, that's really x equals y squared minus x equals 0, which is just giving us y squared. And my larger radius is going to be 4y minus 0, or x equals 4y minus x equals 0. And then it's the same thing again and again and again. Our volume is going to be pi integral from 0 to not 16, right? Because our upper point here was 16 comma 4. The x values went from 0 to 16. The y values are going from 0 to 4. Big radius squared. Oops, that's not the big radius squared. So let's say I did that and I really didn't want to like erase it because it's a pen and I can't, or scratch it out. I could do this, although it's kind of lame, but I'm going to do it anyway. And put absolute values around it. I would probably not actually really do that. It feels like garbage. I would probably rewrite it as pi integral from 0 to 4 of the big radius squared minus the smaller radius squared dy. But if you accidentally subtracted them in the wrong order and ended up getting a negative answer, you could then go back and slap absolute values around every single thing and eventually say it's the positive. Yeah. Yes, an area, a volume, an arc length, a surface area should all end up being positive results. So if you're ever getting negative something, it's possibly made an error. I mean, it's probably made an error somewhere. Hopefully the error is you just subtracted things in the opposite order, which you can fix by just changing the sign. But if you made some other error that led to a negative, then it's harder to fix. You have to go back and look. Okay, two more of these. We're going to go around the line x equal to -3. If we do that, let's see. So, yeah, drawing this picture again and again and again. So now our axis of rotation is over here. And so all of our radii should have gotten 3 larger. We move the axis of rotation 3 further away. And they do. When we draw our horizontal strip, my inner radius is just going to be my closer function, which is x equal to y squared, minus my axis of rotation, which is -3. And my outer radius, which is to the further away function, is going to be my further away function, which is x equal to 4y, minus my axis of rotation, which is -3. It's always a difference. So then our volume would be pi integral 0 to 4 larger radius squared, which I will simplify this one time, 4y plus 3 squared minus my smaller radius squared, which is y squared plus 3 squared. I will point out, again, it is important to draw it, right? I wouldn't know which of these was further away from the x-axis without having drawn it really. Or at least I'd have to think about it more than I really want to. So always, 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 I would say you want to draw the region. So now I want you all to try this last one on your own. Same region, but now we're going to go around the line x equal to 5. I feel like I said something stupid here. He did. It's not too terrible. We're gonna fix. So the problem with x equals 5 is for some reason I had in my mind that this point of intersection was the wrong thing. That point is 16 comma 4. And what I've done here is something that we're not allowed to do, which is that the axis of rotation can't go through the region. I've drawn it wrong, right? X equals 5 would be like over here. So what I'm going to change it to, I'm just going to make it bigger. I'm going to make it x equals 50, which would certainly be look much further away, but we'll live with that. So let's see here. Our larger radius should be 50 minus the further away function, which is y squared. Our smaller radius should be the difference between 50 and the closer function, which is 4y. So our volume should be pi times the integral from y equals 0 to y equals 4 of 50 minus y squared squared minus 50 minus 4y squared dy. And part of the reason we just set these up is just because it's not like it's hard to integrate that. It's just messy, right? You have to multiply it out and then you have to differentiate each thing. And there's probably gonna be like 5 or 6 terms, and then you're just gonna have funky powers and funky denominators. So we usually just focus more on setting these up. But this is something that is totally well within your ability to integrate. It's just a pain.
Like an example and stuff, just we.
You should read the instructions because almost anyone who's going to ask you to do something like this on an exam doesn't want to grade the mess of work that will happen when you try to actually calculate it. So almost every time, either the volume integral is going to be relatively simple to integrate and actually calculate, or it's going to be a mess like this, and then you're going to write the words set up and do not evaluate. So just set it up, don't actually integrate it and find the volume. Or if you really had to, ugh. So let's pretend like they wanted me to actually do this one, even though this is really awful. I would multiply it out. Ugh, ugh, I'm regretting it already. So I'd multiply it out. I'd get 50 times 50 is 2,500 minus 100y squared plus y to the fourth minus also 2,500. Cool, those are going to cancel out. Negative 200, negative 400. Yeah, 4 times 50. Yeah. Plus 400y and then minus 16y squared. Those cancel. I can rewrite it as pi integral from 0 to 4. Let's see, I've got y to the fourth. I've got minus 100y squared minus 16y squared, so minus 116y squared. And then finally, plus 400y. And I would do this. I would integrate it. I'd get pi times y to the fifth over 5 minus 116y cubed over 3 plus 400y squared over 2 from 0 to 4. And then I just plug in 4 and stop there. That's it. Well, I'd say it's pi times 4 to the fifth over 5 minus 116 times 4 cubed over 3 plus 200 times 4 squared minus 0, 0, 0. And I would be like, cool, good enough. I wouldn't actually try to simplify that expression any further. Mm-hmm.
These will find for X or find for Y.
Mhm.
I just kind of get confused on how do you know which one is the outer and inner region.
So that's where the picture comes into play. So in this one here, I can see that the outer radius is the distance between my axis, x equal to 50, and the further away function because it's touching the blue function right there. So in this one, for this axis of rotation, if I just move out that way, I can see that the closer function is the red function and the further away function is the blue function. But really, 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 it's based purely on drawing the picture accurately enough so that we can see the things. So that's why I'm emphasizing draw the picture, draw the picture, draw the picture. Let's see. I feel like there's something else I want to say here. No, again, I'll repeat myself here. For disk/washer method, the strip that you draw in the region, which we usually put kind of in the middle, should always be perpendicular to your axis of rotation every time. On the other hand, sorry, I didn't mean to like take that away from me. I was just like, I want some flair. So let's say we were forced to do this next problem. We want to set up an integral for the volume of the solid formed when the area between, which way do I want to do this? I could go that way. Trying to think about it. No, we'll do it that way. Between y equals root x, y equals 6 minus x, and yeah, we'll do the same. X equals 0 is revolved around the y-axis. So let's draw the region. So y equals root x, easy enough. And y equals 6 minus x is a straight line with a y-intercept of 6 and an x-intercept of 6, so it looks something like this. Now we have to be extra careful here because it looks kind of like there's two valid regions to choose from. But the region that we're looking at should be the one that is bounded by all of the curves that were mentioned. So y equals root x is the boundary, y equals 6 minus x is the boundary, and x equals 0, which is the y-axis is the boundary. So my region is this deal right here, not that part right there. If I had said the x-axis instead, then it would be that one. So we're going around the y-axis. So since we're rotating around a vertical axis, if we were going to use the disk method here, disk because my region is flush with the axis of rotation, I would need to use two integrals because below this line here, my radius is just the function, which if I solve for x in terms of y, it'd be the function x equal to y squared. Whereas up here, my radius is the function y equals 6 minus x, or x equals 6 minus y. And I really don't like doing two integrals when I don't have to, but we could, right? So just to point out, the volume here using two integrals would be the integral from, sorry, pi times the integral from 0 to, oh, what's that point there? Well, let's think, I don't want to set 6 minus x equal to the square root of x and square both sides. I just don't feel it. So let's pick some nice values of x that are easy to take the square root of. You could try 0. Okay, square root of 0 is 0. 6 minus 0 is 6. They're not the same. You could try 1. Square root of 1 is 1. 6 minus 1 is 5. You could try 4. Square root of 4 is 2. 6 minus 4 is 2. Oh, that's the number. So this point is the point 4 comma 2. X is 4, y is 2. Or you could have set them equal to each other and squared both sides and found the solutions, but there would be two solutions and only one of them is right. So here, my volume of my lower half is going to be the integral from 0 to y equals 2 of pi times my radius, which is y squared squared dy. That's my lower volume. Plus my higher volume is going to be pi times the integral from 2 to 6 of, now my radius is the function x equals 6 minus y squared dy. How do I know it's in terms of y? Because my strips are horizontal. So whatever way your strip is oriented, its thickness, the change in y, or if it's a vertical strip, the change in x, that's telling us what variable we're using. Okay, I don't want to do it this way though. What I really want to do is I actually would prefer to use a vertical strip. And so to use a vertical strip, we're going to use the shell method. I have enough room here, yeah. So, same region. Yeah. So now the idea is that instead of using a strip that's perpendicular, we're going to use a strip that's parallel to the axis of rotation. And the idea is that when we revolve that vertical strip around an axis that's parallel to, we're not going to get a disk anymore or a washer. We're going to get a cylindrical shell. Literally, you can think of it as like a pipe, like the water goes through. Like the pipe part is actually the cylindrical shell. It's got a little bit of thickness, but it's mostly hollow. Same deal with our cylindrical shell here. So when we rotate this around, and I didn't really leave myself enough room to do this the right way, but I can make it fit. So the idea is we're rotating this around the y-axis. So you get a little cylindrical shell, right? The shell of a cylinder. Not the whole cylinder, just a bit of it. So what's the volume of that? Well, if we think about this thing, if we were to kind of say, cut it on the side and unravel it, it would look kind of like this. Where the thickness of this rectangular prism is dx. And the height is your top function minus your bottom function. And the length is the circumference of our cylinder, or the circle that's the top cylinder. That circumference is 2 pi times whatever the radius is. And the radius is how far the strip is from the axis of rotation, which is almost always just whatever variable you're using. I should say, if it's one of the normal axes, either the y-axis or the x-axis, it's just x or y. Because it's just saying how far is x from the, oh, it's x away. So here, my radius is just x. It's how far that strip is from the y-axis. So in this problem, I would say for the shell method, very generically, the volume is going to be the integral of 2 pi times the radius times the height times d whatever. We're doing dx this time. Again, the radius is the distance to the axis of rotation. The height is literally how tall the strip is. And the dx is the thickness. So again, right, you've got 3 dimensions multiplied together. Length, height, thickness, which makes sense because it's a volume. So then in this particular case, the setup for a volume is going to be, we usually put the 2 pi out in front, 2 pi times the integral from, my strips go as far left as 0 to as far right as 4. My radius is just x. My height is the top function, which is 6 minus x minus the bottom function, which was the square root of x, dx. So let me say a little bit more here. The idea is that x is going from 0 to 4. So for example, if x were equal to 3, then the radius would be 3, right? It would be 3 away from the axis of rotation. The height of my strip would be 3 minus the square root of 3, and the thickness would be dx. And as x varies, your height changes and your radius changes. But I'm really just trying to make sure everyone's clear with the fact that the radius really is just whatever value of x we happen to be at, as long as the axis of rotation is the y-axis. Question, yeah.
Well, does that mean like the axis of rotation will change as like we set it equal to 0?
So let me answer your question with an example. So let's say we wanted to do the same one, but now we wanted to rotate around. So same region, rotated around. First we'll do x equal to -3. So here's how this is kind of going to look. Take my region, which looks like this. And so here's my axis of rotation. I'll point out I haven't been drawing the volumes, right? Like technically for this one here, we could have drawn the volume and like kind of doubled it over here and made it look like that, and then tried to give it some sort of like, ooh, that's not the best I've ever done. Right? You could try to make it look, it kind of looks like a top or like a little spinny. Did you guys ever see what's that movie, Inception? Remember the thing that got like spun around? It kind of looks like that a little bit, kind of. But now if we move the axis of rotation away and we rotate this thing, it's gonna look much different because now I'm gonna go 1, 2, 3, and it's gonna be like so now here's my volume. So it's kind of some weird like thing with the whole cylinder cut out from the center. So it's some solid with a hole in it. Hole is not the right word though. It's a solid with a hole punched through it all the way. It's that one. But we don't need to draw. So the reason I haven't been drawing the pictures of the volumes at all is because we don't need the pictures of the volumes to find what the volume is. So I don't love this picture personally, but fine. So here's my vertical strip in my region. And my region is still just this part right here. And so now this is my radius. So before my radius was X, because what I should have said before is I'm imagining this strip is located at X. Like this is X on the X axis. But now X is the distance from there to there, right? From the Y axis. I know, let me be a little bit more circumspect here. Let me label things maybe. Here's my Y axis. Here's my X axis. So my distance X is just how far it is from the origin to wherever I'm drawing my strip on the X axis. My radius is going to be 3 larger than that. So here my radius should be equal to X minus 3 or X plus 3, right? My radius got 3 bigger. And really nothing else changed. So now using the shell method, my volume should be 2 pi times the integral of my radius times my height times my dx. So in this case, it's going to be 2 pi. The integral is still from x equals 0 to x equals 4, because that's still the point 4 comma 2. My radius is now, instead of x, it's x plus 3. My height is still the same as it was before. It's still the top function, which was y equal to 6 minus x minus the bottom function, which is y equal to the square root of x. So it's x plus 3 times 6 minus x minus the square root of x dx. So, yeah. And then if we were to say do one other one here, still the same region. Do I have enough room? Yeah, I probably have enough room. Sure. So now, same region, but now around x equal to, say, 6. Now here's how things are looking. I'm not going to draw the whole volume this time because I don't feel like that's particularly useful. If we draw our region again, and we're still thinking of a vertical strip because our, well, I should say my axis of rotation is over here at x equal to 6. My strip for the shell method has to be parallel, right? Shell rhymes with parallel, shell parallel, shell parallel. So if what I should really say is when you're doing a volume of rotation, yeah, you get to decide unless they told you how to do it. So the real process is decide which strip is better for you to draw. And then if your strip happens to be parallel to your axis, oh, it's shell method. If your strip happens to be perpendicular to your axis, oh, it's washer or disk method. So here, since I'm going around the x equals 6 line, well, I want my strip to be parallel, or I should say I want my strip to be vertical because the horizontal strip means I have to use 2 integrals, and I don't want to do that. So now, let me label this a little bit better here. This strip is located x away from the origin, or x away from the y-axis. My radius now is this distance here. The difference between my strip location and my axis of rotation. So here, the radius is going to be 6. No, I don't love that choice, James. It's not terrible. I just don't like the choice that my radius is going to look the same as one of my functions. Like, I just feel like that might be slightly confusing. Let's call the radius 8 instead of 6. Sorry, I mean the axis of rotation. Let's call it 8 instead of 6 because it's easy to turn a 6 into an 8. Cool. So now my radius of my cylindrical shell is going to be 8 minus x. And the order of subtraction is important here. 8 minus x is positive. X minus 8 would be negative, and you would get a negative volume if you subtracted it in the wrong order here. So then our total volume, once again, 2 pi integral r times h times dx. I really do think of it as 2 pi r and then h and dx, and 2 pi comes out, whatever. So here our volume is going to equal 2 pi integral still from 0 to 4. My radius now is 8 minus x. My height is still the top minus the bottom, which is 6 minus x minus the square root of x dx. Oh, shell method. Sure. Okay. Let's look at another example. So we want to find the volume obtained by rotating the region bounded by, what have I got here? Y equals 8x, y equals 16, and y equals x squared. Now I've done this, I made this mistake before. Sorry, bounded by y equals 8x above by y equals 16 and y equal to x squared in quadrant 1. Around the x-axis. Okay, so let's see if we can draw this thing carefully. I say to myself. So y equals 8x. I probably, when I start drawing this, I do start thinking about like where things are going to intersect. So like y equals 8x and y equals 16, those are going to intersect when x is 2. So y equals 8x is going to look, pretty steep. And y equals 16, is going to be somewhere up here. And the point of intersection should be the point 2, 16. Yeah, we definitely have looked at this before. And then it's bounded above by y equals 16 because on the last time when we did this one, I just said bounded by that. And then we're like, well, James, is it the part that's below the blue line or above the blue line? So it's not the region that's up here where these intersect again later. It's definitely this region here. Bounded above by y equals 16 and also bounded by y equals 8x and y equals x squared in quadrant 1. And we're rotating around the x-axis. But regardless of the axis, if we're trying to make this into as little work as possible, what kind of strip do I want to use? Do I want to use a vertical strip or do I want to use a horizontal strip? I'm not sure. So here's kind of the defining piece of information. Does one of them make you have to do more than one integral? And in this case, a vertical strip would require 2 integrals because if we use a vertical strip, the top function changes, right? A vertical strip over here, the top function is y equals 8x. A vertical strip over here, the top function is y equals 16. We'd always prefer to pick a strip where its ends don't ever change. So here, top and bottom, well, the bottom's always the same, but the top changes. Shoot. On the other hand, if we draw a horizontal strip, no matter where we draw it, the left boundary will always be y equals 8x, and the right boundary will always be y equals x squared. So I'm choosing a horizontal strip, which then means, since I'm rotating around the x-axis, I am forced to use the shell method. I don't have a choice. I mean, I do have a choice. I could choose to do it the other way and do 2 integrals, both using the washer method. That's not the choice I want you to make. It's not the choice I want to make either. So since we are using this, we're saying, okay, now this strip is located at a height of y above the axis of rotation. So our volume is going to be the integral of 2 pi times my radius times my height times my thickness, which is dy. When I'm thinking shell, I always just write that down. It's 2 pi r times h times d whatever. I know it's dy because my strip has a little bit of change of y for the thickness. The height of my strip, or how long it is the right function minus the left function. But since I'm in terms of y, they better be in terms of y. So y equals x squared becomes x equals root y. It is positive root y. And y equals 8x becomes x equals 1/8 y. So my height is right minus left. So it's root y minus 1/8 y. My radius is just how far away this strip is from the axis of rotation, which is just y. And my limits of integration, well, my strip goes as low as 16, sorry, as low as what? As low as 0 to as high as 16. So our volume integral should be 2 pi times the integral from 0 to 16 of y times root y minus 1/8 y dy. Which actually isn't that terrible, right? If you actually multiply this out, you'd be doing 2 pi integral from 0 to 16 y to the 3/2 minus y squared over 8. You can totally integrate that and get 2 pi times 2/5 y to the 5/2 minus y cubed over 24 from 0 to 16. Sure, that's something. You get 2 pi times 2/5 times 16 to the 5/2 is 4 to the 5th, which is 1024. Minus 16 cubed is 2 to the 12th, which is 4096. So there's an answer. But again, stop here or plug it in and don't worry about the math. These happen to be nice numbers that we might know. Thank you so much. All right. Let's see. Anything else I want to say about shells? Not really. That's kind of the whole story on shells. So really, I'll say again, for volumes of revolution, you get to pick the strip. You want to make the choice where if you slide that strip either up and down, in this case, the left and the right boundary are always the same, or if it's a vertical strip, you slide it left to right, the top and the bottom boundary are always the same. Since that wasn't true here, right, my vertical strip was not the best. Sliding left to right wasn't good to go. So I slid up and down instead. I used it for a horizontal strip. Yeah. Let me actually go back. We'll not go back, but we want to do one more. Yeah, we'll do one more. So region bounded by y equals 6 minus x, y equals root x, and now instead of x equals 0, y equals 0. Thank you. Yes, of course. So almost the same region we were dealing with the example before this last example, except here's y equals 6x, 6 minus x. Here's y equals root x. And here's y equals 0. So now we're looking at this region here. So on your own, draw the right kind of strip. Or think about what it should be if you didn't draw the picture, which is totally fine. You didn't draw the picture. All right, I'm definitely drawing a horizontal strip because no matter where I draw it, the left boundary is that green function, the right boundary is that right function. If I drew a vertical strip, halfway through the top would be green and the other halfway through the top would be red. And I don't want the top of my vertical strip to change boundaries from left to right. So I don't want to use a vertical strip. I could, but I don't want to. Okay, so if we rotate around the y-axis, are we using the shell or the washer method? Washer, because our strip is perpendicular to our axis of rotation. So on the y-axis, our volume is going to be pi times the integral of the big radius squared minus the little radius squared dy. I should probably write down what my functions are. This is y equals root x, or x equals y squared. This is still y equals 6 minus x, or x equals 6 minus y. So in this integral, my larger radius is the red function, 6 minus y. My smaller radius is the green function, y squared. my limits of integration are from as low as y equals 0 to as high as whatever this point of intersection is, which I still believe is 4 comma 2. So the upper limit of integration should be 2. If on the other hand we go around the x-axis, now we're using the shell method. So now our volume is going to be 2 pi times our radius times our height times still dy. It's got to be dy because my strip is horizontal. So now my limits of integration don't actually change. Still going to be from 0 to 2. But now my radius is how far away the strip is from the axis of rotation, which is just y. And my height is how long that strip is, which is the right function minus the left function. That's going to be 6 minus x minus the square root of x. Sorry, almost. So the right function, but if I'm going to have a dy over here, I better not be having x's in my integral. So that should have been not y equals 6 minus x, but x equals 6 minus y. And not the square root of x here, but x equal to y squared. Sorry about that. Let's write it again just so it looks pretty. 2 pi integral from 0 to 2, y times 6 minus y, the right function, minus y squared, the left function. So, lots of washers and shells and discs. Practice, 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 right? I mean, the way to get the way to get it down is to just do it a lot. So, moving along to arc length. So, arc length. So I can make this look pretty here. Or how long some curve is. So let's say we have some curve that looks like this. And we are going to, I'm going to write some words here, I guess. Imagine a particle moving along a curve. So maybe, maybe it starts here and moves in this direction to here, and then to there, and then to there, and so on and so on. Just keeps moving along the curve in one direction. The arc length of that curve, or the arc length it travels, we will call S. So that the derivative of S with respect to time is the velocity of the particle. And now what we're going to do is we're going to zoom in on one little section. So just like every other kind of integral thing we've calculated, you are adding up a bunch of little things, a bunch of rectangles, or a bunch of slices of washers, or a bunch of cylindrical shells. Also, there's really good pictures of cylindrical shells in the book where it's like there's like a really skinny cylinder, and then there's like one that's around it and around it and around it and around. So you're adding up all these like shells. There's some really great pictures that you have available to you. I encourage you to look at them. They are helpful. But the idea here is we're going to kind of look at just this little section from here to here, where if we focus in on that, well, I'm going to zoom in. So let's make it a little bit bigger. We're kind of like that. So that section there looks like that, kind of. And the idea is that this length, which is a small change in S, the total arc length, we could think of as, well, this horizontal distance is a small change in x, and this vertical distance is a small change in y. So we could either say that, or we could say that ds dt is the particle's velocity in the s direction. Dx dt is how much velocity, sorry, ds dt is the velocity in the s direction. Dx dt is the velocity in the x direction, and dy dt is the velocity in the y direction. And we could use the Pythagorean theorem to say, well, essentially, this third side, although it's not actually the hypotenuse of that triangle, it's close enough, right? It's approximately it squared is approximately dx dt squared plus dy dt squared. And if you make it small enough, it's close enough. So then what we're going to do is the following. We're going to say that ds dt is equal to the square root of dx dt squared plus dy dt squared. And then we're going to say that just ds is the square root of dx dt squared plus dy dt squared times dt. And then to get the total arc length, we're just going to add up all the little ds's. So the total length s is equal to the integral of ds, which is not what we actually finish with, but I want to point out there's like 3 different arc length formulas. This is where I always start. I say, oh, if I want to find the arc length, I'm just going to integrate ds. But then ds is this or one of 2 other things. So we can say that, and we've got some limits of integration, right? Like here we're starting at, say, like t equals a, we're ending at t equals b. So it's going to be the integral from a to b of the square root of dx dt squared plus dy dt squared. Now I'll point, oh, what? This something here. It's not. Okay, whatever. So let's, sure. So this is fine for functions that are defined parametrically. For example, here's a fun one. Let's say we have our x as a function of t equal to cosine of t, and y as a function of t equal to sine of t, and t goes from 0 to pi. Well, all I'm describing to you is the top half of a circle, right? If you think about the unit circle, the coordinates of the unit circle are cosine theta, sine theta. So when t is equal to 0, I'm getting cosine of 0, sine of 0, or the point 1 comma 0. And then when t is equal to pi over 2, cosine of pi over 2 is 0, sine of pi over 2 is 1. And then when t is equal to pi, cosine of pi is -1, sine of pi is 0. So I'm just saying, what's the arc length of that curve? That's what I'm, well, I actually said that. What is the arc length we have described? Well, we already know the answer, right? The circumference of a circle is 2 pi times the radius. So the arc length of half of a circle is just going to be half of 2 pi times the radius. So we're expecting our arc length to be 1/2 of 2 pi times 1, which is just pi. Let's see if this is borne out. So the arc length should be the integral from t equals 0 to t equals pi of the square root of the derivative of cosine squared plus the derivative of sine squared dt. Oh, but check this out. That's going to be the integral from 0 to pi. This cosine's derivative is negative sine. So we have the square root of negative sine of t squared plus the derivative sine of t is cosine of t squared dt. But what's sine squared plus cosine squared? 1. So we really have the integral from 0 to pi of the square root of 1, which is 1. We integrate 1, we get t evaluated from 0 to pi. We get pi minus 0, which is pi. Now, do you need to use the arc length integral to find the length of half of a circle? No. But is it good to see that it does give us the answer we expect? Definitely yes. Okay, but what if you're not given the function parametrically? Well, here's what you do. So if the curve is given by y as a function of x instead of a parametric form, we can easily parameterize in exactly the following way, by letting x equal t and y equal f of t. So then here's what happens. Your ds, which is equal to the square root of dx dt squared plus dy dt squared, just ends up becoming the square root of 1 plus f prime of t squared. I forgot the dt here, sorry. Or we could just use the original variable and say it's f of x instead of f prime of x instead of f prime of t. So usually what we do is if y equals f of x, the arc length formula is going to be is s equal to the integral from whatever your limits of integration are of the square root of 1 plus, you can either write it as f prime of x or as dy dx. People usually write it as dy dx. Or f prime of x. Either way. And then if x is a function of y, you can do it the other way. So if x is a function of y, it'd be the square root of 1 plus dx dy squared, so dy dx squared. So there's like 3 different versions of the arc length formula, which is kind of annoying, but it's totally fine. So let's look at an example. Because yeah, there's all these formulas, but we need an example. So let's say we want to find the length of y equal to x to the 3 halves from the point 0, 0 to the point 4, comma 8. All right, doesn't seem too terrible. So we know that s should equal the integral of ds. Which again, I know that's kind of a weird way to start off, but I do think it helps me remember what ds is. So this is going to be the integral. Since we're doing things in terms of x is going to go from 0 to 4. And it's going to be the square root of 1 plus the derivative of my function. So 3 halves times x to the 1 half squared dx. Okay, that's not so bad. So rewriting that, it's going to be the integral from 0 to 4 of the square root of 1 plus 9/4 x dx. We could do a u sub here. We could let u equal 1 plus 9/4 x. My du is going to be 9/4 times dx, or 4/9 times du is going to equal dx. So I can rewrite this as the integral of the square root of u times 4/9 du. And I'm going to change my limits of integration. If x is 0, u is going to equal 1 plus 0, which is 1. If x is 4, u is going to equal 1 plus 9, which is 10. So my new limits of integration are 1 to 10. and I ended up getting 4/9 times the antiderivative of u to the 1/2 is 2/3 times u to the 3/2 from 1 to 10. Simplifying a little bit, I get 8/27 times 10 to the 3/2 minus 1 to the 3/2. And that's my final gross answer. So here I will point out these types of integrals specifically are why it was probably a good idea for us to have talked about all the different integration methods before we do things like this. Because if I asked you something seemingly innocuous, like the arc length of y equals x squared from 0, 0 to 3, 9, you might think, well, that's not going to be so bad. You mean you just did one similar? It seems like it should be. Well, let's find out. So my arc length is going to be the integral from x equals 0 to x equals 3 of the square root of 1 plus 2x quantity squared. And now I'm not feeling super hot about this because that's the integral from 0 to 3 of the square root of 1 plus 4x squared. And that's looking an awful lot like a trig substitution. In fact, I would go back to this iteration of it and say, hey, look, I want that part there. I want 2x to equal tangent of theta. So that I get 1 plus tangent squared. And this problem's super ugly. I don't really want to do it. Let me show you what happens. So we rewrite this as the integral. I'm not going to worry about this for a second. We get the square root of 1 plus tangent squared theta. And then since x is equal to 1/2 tangent theta, my dx is equal to 1/2 secant squared theta d theta. So I get a 1/2 secant squared theta d theta here. And then, fun times, this is going to be 1/2 times the integral of secant times secant squared, which is secant cubed, not secant cubed, which is ugly. It is doable, but it's gross. And then my limits of integration also are not super pretty because well, actually they're not super bad. If x is 0, then theta has to be 0 because tangent of 0 is 0. But if x is 3, that means tangent of theta equals 6, which means theta is the arctangent of 6. That's terrible. We shouldn't finish this problem. We should look at something else instead. So what I'll tell you typically happens with these arc length problems is you either have something that works out relatively easily, like something simplifies nicely, or you have one that has the following kind of pattern. Not that terrible thing. The next pattern we're about to talk about. So let's look at, for example, the arc length of y equal to x to the 4th over 4 plus 1 over 8x squared, where x is between 1 and 2. And before we start writing down our integral from 1 to 2 of ds, I want to figure out what's going on with ds. So I know that ds is equal to the square root of 1 plus my derivative squared. Okay, the thing that's about to happen happens often. So when we find our derivative and square it, what we're going to see is that our derivative squared has a negative 1/2 as the middle term. So check this out. My derivative is 4x cubed over 4 plus, that's a 1/8 x to the negative second. The derivative is minus 2 times 1/8 times x to the negative third. If I simplify this a little more, that's going to be x to the third minus 1/4 x to the negative third. Now I'm going to square it. So my derivative squared is x cubed minus 1/4 x to the negative third squared, or just multiply by itself. And when we FOIL this out, look what happens. X cubed times x cubed is x to the sixth. X cubed times negative 1/4 x to the negative third. Well, x to the third times x to the negative third is x to the 0, which is 1. So we get a 1 times the negative 1/4. So we just get a negative 1/4. But we get that twice. So we get it from these two multiplied together and from these two multiplied together. And then finally, the last term is negative 1/4 times negative 1/4. So it's positive 1/16 times x to the negative 6. So simplifying this one more step, it's x to the sixth minus 1/2 plus 1/16 x to the negative sixth. Okay, here's the special thing that happens when you get this negative 1/2. When you then add 1 to that, check it out. 1 plus my derivative squared is going to be x to the sixth plus 1/2 plus 1/16 x to the negative sixth. And then that factors. It factors in almost exactly the same way it was factored before, except now the middle sign is positive instead of negative. So this is exactly going to factor as x cubed plus 1/4 x to the negative third times x cubed plus 1/4 x to the negative third. And then if you're taking the square root of that, well, the square root of something squared is just the something. So that's the pattern we look for in these problems, is you're hopeful when you see something like this, where it's like two kind of weird things added together, you're hoping that when you take the derivative and square it, the middle term is negative 1/2. So then when you add the 1/2, it factors back almost exactly the same way, and then the square root's super nice. So here's what we end up getting. We end up getting the integral from 1 to 2 of the square root of, I'm not going to write all this down again. My 1 plus dy dx squared is that. It's the square root of x cubed plus 1/4 x to the negative third squared. Oh, but the square root of the thing squared is just the thing. So this is just the integral from 1 to 2 of x cubed plus 1/4 x to the negative third. Now we anti-differentiate, and we get x to the fourth over 4 minus x to the negative 2 over 8. Evaluated from 1 to 2. Or if you prefer, x to the fourth over 4 minus 1 over 8x squared, 1 to 2. So it almost feels kind of silly because we've literally done all this work to end up with practically the same function we started out with. And unfortunately, you do have to show them. So what I'll say is when you see something like this, it is very, very, very likely that after you've done all of this work, the function that will be your integral will be the same function as this with the middle sign changed. Almost always. And then we plug in and we get 16 over 4 minus 1 over 8 times 4 minus 1 over 4 minus 1 over 8. And I wouldn't do anything else with it. Bless you. So kind of ridiculous. There's lots of functions that do this sort of thing. So yeah, we have time for one more, or at least to look at one more. So another example of this would be something like, make sure I get it right here. X equal to natural log of y minus, sorry, I have to make sure it comes out right. 1/8 y squared. Looking at this, we want to find the arc length for y between 1 and 2. So when I see this function, to me, that just reeks of this pattern happening. Like when you have one piece minus another piece, really the key thing that I look for is if I take the derivative, are the powers going to be opposite signs? So if I take the derivative here, my dx dy is going to be 1 over y minus 1/8 times 2y. Or in other words, it's going to be y to the negative first minus 1/4 y to the first. Oh, that's looking really good. So then I'm going to square it. And I do kind of think it's worth doing all this work kind of step by step instead of just starting with the integral. So squaring it, we get y to the negative 1 minus 1/4 y times y to the negative 1 minus 1/4 y. We multiply it out, we get y to the negative second. We get a negative 1/4 minus another 1/4, which is a minus 1/2. And then we get plus 1/16 y squared. We add 1. That's going to become y to the negative second plus 1/2 plus 1/16 y squared. Notice, right? The change. And then we factor it back as y to the negative 1 plus 1/4 y 1 squared. And now I think we're ready to do the integral. I will point out also, I know I didn't say it, but this is the other version of the formula, where instead of y is a function of x, x is a function of y. So here our arc length is going to be the integral from y equals 1 to y equals 2 of the square root of 1 plus dx dy squared dy. But now we can simply say that that's going to be the integral from 1 to 2 of the square root of y to the negative 1 plus 1/4 y on d squared dy. Square root and square root undoes each other. So we get the integral from 1 to 2 of y to the negative 1, or 1 over y, plus 1/4 y dy. We integrate. The integral of 1 over y is the natural log of, I'm just going to write y here because I know my y's are already positive, so I don't need the absolute value. Plus 1/4 y squared over 2, or 1/8 y squared. And again, look, we did all this work to get to back to essentially where we started. Which again feels kind of like we spent time doing something we didn't need to do, but we did. And then we plug in our limits of integration. So we get the natural log of 2 plus 4/8 minus the natural log of 1, which is 0, plus 1/8. So simplifying, our final answer is going to be the natural log of 2 plus 3/8. I would say the better reason to keep this process in mind is because when we talk about surface area, it's kind of like a combination of the shell method and the arc length. Surface area is going to be the integral of 2 pi r times your thickness. So when we talk about surface area next time, I'll point out that when you have some sort of, I don't know, like if I take some sort of curve and then rotate it around an axis, if I want to find the surface area, what I'm going to think of doing is taking a little section of that curve, which has a length of ds, right? Because it's not just a change in x or a change in y, it's a change in both directions. And then we're going to rotate that around and get like a rubber band shape. And the area of our rubber band is going to be, well, it's the circumference of the circle, 2 pi times whatever the radius is, probably like x or y, in this case x, because it's how far from the y-axis, times the thickness of the band, which is ds. And that ds is the same ds that we just talked about, the square root of 1 plus the derivative squared. So that's that kind of thing we just talked about comes up in these examples as well. So that's mostly why we talk about it for. All right, it's 4:30. I should stop talking. Have a lovely rest of your Thursday.